how to take derivatives of some of the rest of the types of functions that we usually encounter. And when we're talking about the chain rule, the book goes into a lot of descriptions about how to do it, and I simply, they're great. They're great, and I used to really like them, and I've thought of easier ways of doing things since then. So we're going to talk about things in terms of composite functions, how to find the derivative of a composite function using the chain rule, how to recognize when you've got a composite function so you can use the chain rule, how to find the derivative of a function using the general power rule, and then how to simplify the derivative of a function using algebra, and then using the chain rule within trig functions. So this is the final rule of how to take derivatives, and it's probably the most powerful. If you've noticed, we've been very, very limited, it might not seem like it, but we have been in what types of functions we've given you. We might have said, hey, take the derivative of x times sine x, but we never said, hey, find the derivative of x times sine of 5x. Okay, does that make sense? We might have said, hey, let's take the derivative of x minus 2 times x minus 3. But we never said, hey, let's take the derivative of 3x minus 2 squared times x minus 3. Okay, it's a little bit more to it, if you can believe that. Okay, so we're going to have to realize that we're dealing with composite functions, and because we're dealing with composite functions, the rules are expanded. And really, we give you the most restrictive cases first, and then we take it out to the most general cases with calculus and taking derivatives, okay? So that's how it goes. So we're working out to the more general rules. So functions that we could take the derivative of without the chain rule would be things like x squared plus 1. With the chain rule, we can do the square root of x squared plus 1. Without the chain rule, we were stuck with something like sine x. But with the chain rule, we could do like sine of 6x. We talked about this one, and this is another example of what we could do with the chain rule versus without the chain rule. So basically, the chain rule states that if y changes at the rate of change in y over the change in u times as fast as u, and u changes so fast with respect to x, then y changes the derivative of y with respect to u times the derivative of u with respect to x as fast as x. That means nothing to you guys, probably. You know, it's just like, oh, those are nice, pretty words. I have no clue what you just said. So they give this really nice example of gears. Now, we tend to not teach gear math as much as we should anymore, right? I mean, whenever you see gears like this, I don't know about you, but I always think of Beauty and the Beast and Belle's father and his inventions and all the gears that he had. You know, do you remember that cartoon? Yeah, this kind of reminds me of that. Okay, so if we are looking at y, u, and x, they represent the number of revolutions per minute of the first, second, and third axles. So axle 1 goes y revolutions per minute. Axle 2 goes u revolutions per minute. Axle 3 goes x revolutions per minute. Okay? So we want to find the number of revolutions of the first axle compared to the second axle. Okay? I have a new feature. I have this. Look at that. I am so happy with this. I just downloaded the new version since I saw you guys. It's so cool. Okay, so if we look at axle 1 versus axle 2, we can see that axle 1 is going to go around many more times, or in one revolution of axle 2, axle 1 will go around more, right? And when we're looking at axle 2 versus axle 3, well, that's entirely different as well, right? So, because the circumference of the second gear is 3 times that of the first, that first axle has to make 3 revolutions in order to turn that second axle 1. So dy over du, or the amount of change in the first with respect to the amount of change in the second axle, is 3. Similarly, the second axle must make 2 revolutions to turn the third axle once. Where's the third axle? Gear 4, yes. Okay. So 2 with respect to 1 of those, okay? So combining these 2 results, we know that the first axle must make 6 revolutions to turn that third axle once. So we can write that the change in the first axle with respect to the third axle is equal to the change in the first with respect to second times the change of the second with respect to the third, okay? So what does that mean for us? Well, when we think of our functions, they give it in 2 different formats here, okay? So if I want to look at the change in y with respect to x, okay, I want to look at the change in y with respect to some middle function and the change in the middle function with respect to x. So the key to all of this is understanding that all of this is equivalent to that chain rule, okay? And I'm not going to go through any of the math with regard to that, but let me just say that what we have here is kind of the derivative of an inner function versus an outer function, okay? So we have the outer function f, right? But into that outer function, my input is g of x, right? Okay, so that's a composite function. We know f of g of x. We've done this before, right? Well, the derivative of that composite function is equal to the derivative of the outer function where that inner function does not change, still is g of x, times the derivative of the inner function, which is super simple. It doesn't look like it in all this math-ese, but it's super simple. So we take the derivative of the outer function and leave inner function alone. And then multiply by the derivative of the inner function. So the key is knowing what are your outer functions and what are your inner functions. So your outer function, you know, is kind of a structure function, right? So if I had the function 3 times x minus 2 squared, right? My outer function is what? Yeah. And my inner function is x minus 2. Okay? So if I wanted to take the derivative of this, then I would take the derivative of the outer function. What's the derivative of the outer function? 6 times x, right? And I would leave that inner function alone. See how this just goes down to 1, right? And then multiply it by the derivative of the inner function, which is just 1. Okay.
column of like a list of like things that you can do with the chain rule.
Mhm.
Like the square root, like just be square root of x, and then you would do the derivative of the inner stuff.
No, we'll get to something like that here in a second. Okay. So actually, let's just do that one. Where was it? So let's look at all of these. Okay, so if I want to take the derivative of this, I need to rewrite it as y equals x squared plus 1 to the 1/2 power. We good with that? And then we can start taking the derivative. So then y prime equals 1/2, leave the stuff inside alone, to the negative 1/2, we subtract 1, times the derivative of x squared plus 1, which is 2x. Okay. So then when I put this back in nice form, 2x is going to go up on top. I've got a 2 from here that's going to go on the bottom. And I'll have a square root of x squared plus 1 here. So that will reduce down to x over square root of x squared plus 1. Okay. What would y prime be for sine of 6x? Well, I take the derivative of sine x, which is cosine. I leave the inner stuff alone, right? And then I multiply it by the derivative of the inner stuff. What was it? Just 6. So this becomes 6 cosine 6x. Next one. What's the outer function on this one? X to the 5th, right? So when I take the derivative of that, it becomes 5 stuff to the 4th. That stuff is 3x plus 2. And then what do I multiply by? What's the derivative of 3x plus 2? Just 3, right? So that equals 15 times 3x plus 2 to the 4th power. You with me? Okay, you look tired. If you need to stand up, back of the room, walk around, whatever you need to do, to just don't feel constrained to that, okay? If you start slapping yourself, just go home and sleep. I've been known when I'll sometimes take long car rides, you know, when I was up in Minot, I would drive down to Denver and I would drive back up to Minot and stuff like that. And it's a long trip to take by yourself. And sometimes I would just get so tired and I would just be driving in the middle of nowhere, whap, you know, just slap myself in the face just to wake myself up, you know, because I didn't want to die. Then one time it was a really snowy evening and I was just passing Amadon, North Dakota, which the road to Amadon it's straight up from the Black Hills, and then it goes over and then back up to a 94, and then you go over for a while and then up to Minot. So but Amadon's right here. And Amadon is a crazy little town. The first time you go through it, you just want to slam on your brakes, because right outside of town, as you're coming down from the north, right about right here, they've got this police car with a dummy inside. Only as time passes, you kind of see the joke a little bit more, because they parked it there because they don't have any police and they wanted people to slow down, but the car keeps just getting older and older and older, you know, so eventually you're like, yeah, whatever, you know. Anyways, but I was headed up, I just passed Amadon, or I was headed up to Amadon, but anyways, I'm in the middle of nowhere, snowy road. It was in December. I don't know what I was thinking, but I was young and invincible. And all of a sudden, there's this big, huge buck staring me down in the middle of the road. Now, that woke me up. Oh my gosh, that woke me up. Because when I was in missiles, they always said, okay, if you come across a deer, whatever you do not swerve. You just hit the deer. And I was like, okay, I'm gonna hit the deer, I'm gonna hit the deer, I'm gonna die, and nobody's gonna see. I hadn't seen anybody in like 20, 30 minutes on the road. You know, it was cold. And finally, he knew better. He hightailed it out. But gosh, I did not fall asleep after that. It was not fun. Anyways, so there's your funny story to help wake you up a little bit. No. Okay, y equals x plus tangent of x squared. Okay, now this is kind of adding two functions, right? So I'm going to take the derivative of the first. What's that first function? X, so my derivative, y prime, is going to be just 1, right? Okay, and when I'm looking at tangent of x squared, I want to think of that as tangent parentheses x squared, right? That might be a little bit easier, because what's the derivative of tangent? Secant tangent, right? Or secant squared or something? Secant squared, yeah. Okay, plus secant squared of whatever my stuff is, which is going to be x squared, times, what's the derivative of x squared? 2x. And so this 2x would be written in front of secant squared. So this would be 1 plus 2x secant squared x squared. Which if we were writing with this with the parentheses, it would look like secant of x squared squared, right? The whole trig way of showing squareds can kind of mess with people's heads, I think. And so that's why I always try to think about what would it look like if I was squaring that whole secant function with parentheses, okay? So instead of writing it in their little trig way, I write it in the way that makes sense to the rest of algebra. And that helps keep me from making mistakes or getting stressed about the problem, okay? So, yeah, we did those. So that brings us to the general power rule. So we have been talking about lots of different things, but the general power rule is a special case of the chain rule, okay? So basically the general power rule is, a special case of the chain rule, okay. So the general power rule says, this is what happens when I didn't get my water. I'm thirsty and everything is kind of sticking together in my mouth. So when I have some function to a power n, the derivative of that function is going to be the n times the function to 1 less power times the derivative of the function. Okay? So I have a little acronym for this, because this is an inner part of my function, right? So I call this the derivative of the inner part, or dip. Okay? So I always say, don't forget the dip, because everybody else, they'll do all of this great, and then they'll forget that last multiplication part. So I always say, don't forget the dip, because if you're going to make a mistake, that's where you're going to make it. Just letting you know. You don't mean to, it just happens. So don't forget the dip. Pardon? Okay. Just makes you hungry when I say it. Bring some chips and dip, you know. Yeah. I like how I relate difference quotient to Dairy Queen. Chain rule to chips and dip. I just have food on the brain. Okay. So here we have this problem here. We have f of x equals 3x squared minus 3x minus 2x squared quantity cubed, right? So then f prime, or the derivative of this, will equal what goes up here? Squared times the derivative of that mess, which was right. See, that was how much they used. That was how much I used. It's all good. Okay. Let's do, I think it's important to do more of these. So we'll do number 7. Actually, we'll do number 5. And that is f of x equals the cubed root of x squared minus 1 squared. And we want to find the derivative of that. So how do I rewrite this without a cube root? Yeah, so I have x squared minus 1 squared to the 1/3 power, right? Is there a way to simplify that even more? Power to a power, I multiply. So that just becomes x squared minus 1 to the 2/3 power, right? Now I'm actually ready to take my derivative. So f prime is going to equal times 2x. Very good. So when we simplify that, that becomes 4x on top, right? The 3 goes on the bottom, and then all that negative 1/3 power goes on the bottom as a cube root. All right. And what do you do if you are looking at your answer that looks like this, and you're looking at your answer that looks like that, and you're just not sure you did it right? Put them both into Desmos. What are you looking for? Same thing. They're not the same thing. You did it wrong. If they are, you did it right. I took this 2 times that dip to get 4x. Okay. Number 6, g of t equals -7 over 2t minus 3 quantity squared. Right? To the -2 power. So then g prime of t is just 2. So that becomes 28 on top. All the rest of it goes on the bottom as 2t minus 3 cubed. Okay. Let's do some problems from the back of the homework. Because they're not always this easy. Okay. Okay, what do we see going on here? What?
Lots of fun.
Lots of fun. What kind of fun?
Whenever you,
No, 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 no. It's a little bit more fun than that.
There's 3 functions.
It's what?
There's 3 functions.
Ah, yeah, there's not just 2 functions. What's happening with some of the functions?
They're being multiplied together.
Yes, which means I have to do what?
The product rule.
Bingo, product rule. What? Product rule. So we got product rule stuff going on. So this function times this composite function, right? Ah, see, this is where I said, hey, you guys are going to sometimes not recognize that it's a product rule or a quotient rule type thing. Yes, I'm totally cruel. Heartless. Okay, so it's first times the derivative of the second, right? So the first times the derivative of the second. Now, how am I going to take the derivative of that purple function? Two x minus 5 to the times just 2. Okay, plus the second function times the derivative of the first function, which is 1. So when they simplify, 2 times 3 times x is 6x. 2x minus 5 squared plus 2x minus 5 cubed. Okay, now I'm going to double check how they want us to, pardon? Okay. Double check that I'm going to give it to you in the right format to match what they will do with no, hold on. Still not out of chapter P. It's a little too far. Here we go. No, okay, so this is where we're at. Okay, we are at a little bit past that right there. Okay, because we kind of did 6x, right? So what they're wanting us to do is factor. That's what I figured they wanted us to do. So if I look at this, I've got 2x minus 5's here and 3 of them there. So I'm going to factor 2x minus 5 squared from each term. And that gives me 6x from the first term, and my second 2x minus 5 from the second term. And then I'm just going to combine like terms. And I'm done. And I've got, why do I do this? Because it gets it down to how many terms? 1. It's a binomial times a binomial, but it's all one term in the overall structure. Okay? And that, if you want a guiding goal as to how do I know when my answer is correct, try to get it to the fewest number of terms possible, and then your answer will be correct in the format that they're seeking with the multiple choice answers. Okay. Now I want to do 28. Okay, so this one is y equals x over the square root of x to the 4th plus 4. Now, what do we see going on with this one? Yeah, the quotient rule. Because, yeah, I'm nice. Now, is there a way to avoid the quotient rule? Usually there is. Did you know that? I could write it as a product, couldn't I? I could do it either way. Okay, I'm going to be cruel and heartless, and we're going to do the quotient rule because you need practice. Y prime. Okay, lower function is x to the 4 plus 4 to the 1/2. Okay. Because it's the lower function, we're not putting that negative in there. Are we good with that? We're just looking at it as a lower function, not with regard to its position. Times the derivative of the higher function plus the higher function times the derivative of the lower function, which is 1/2 x to the 4th plus 4. Oops, I need some more room here. To the negative 1/2 times 4x cubed, all over the lower function squared, which becomes x to the 4th plus 4. So now you see why that's a whole lot nicer. Okay? Just saying. So looking at this, I've got the square root of x to the 4th plus 4 on top, plus 4x cubed times x, which is 4x to the 4th, times 1/2, which makes that 2x to the 4th, okay, over the square root of x to the 4th plus 4 over x to the 4th plus 4. Yay. So what would be nice to do here? Well, there's a couple ways you could handle this. I could deal with just the numerator, or I could kill all my fractions in one fell swoop. One fell swoop thing, which means you take the common denominator and you multiply it over itself. So I'm going to multiply by square root of x squared, x to the 4th plus 4 over 1 over, oops, that. Okay, so that's what I'm multiplying by. Now, what that does as I distribute this is it says the first term is just going to be x to the 4th plus 4. The second term is just going to be 2x to the 4th, right? Everybody good with that? Over the square root of x to the 4th plus 4 times x to the 4th plus 4. So that simplifies to 3x to the 4th plus 4 over x to the 4th plus 4 times square root of x to the 4th plus 4. Yay. It's nasty. Okay. Would this one have been any different if we'd have just done the product rule. Yes.
Why did you get the 2x to the fourth over the square root of x to the fourth plus four?
Okay, so from this mess here, when I take this times x, it's 4x to the fourth, right? Times 1/2 makes it 2x to the fourth. The negative on this means that square root is in the denominator. Okay? So you just kind of have to break it down into the structure of what's going on. Are we good with that? Do you see why I like really hammer? You need to understand negative radicals. You need to understand fractional exponents, negative fractional exponents, how to convert back and forth between the two. Okay? And then let's check back and see if I even got the right answer. According to our solutions manual. Oh, should have been a negative, yeah. Something happened. I missed that negative. I got that one. I just missed the negative here. And somehow I showed it as the thing times the square root instead of to the 3/2 power. That's what I did. I just showed it a different way. So does everybody get that this part here, this is like saying x to the fourth plus 4 to the 2/2 times x to the fourth plus 4 to the 1/2, right? Which makes it x to the fourth plus 4 to the 3/2. Okay? So my minus here messed me up. And so that'll just be negative equals negative x to the fourth plus 4 over x to the fourth plus 4 to the 3/2. And that's a better answer. Okay? You can do it the other way. Huh?
Where did you go?
1 minus 2 is negative 1.
Oh, yeah.
Okay. We good with all of that? It's a lot of algebra. You'll know your algebra by the time you're done with calculus. You'll know you know your algebra. You'll be very confident that your college algebra is solid, like a rock. Okay. Which gets us into the whole thing of sometimes you've got to do a lot of simplifying. Okay. And we've practiced with a little bit of the simplifying. I'm going to erase a lot of this so that we can do some more. Because frankly, that's a lot to take in on the page.
So how do you know if it's a composite function?
So like when you're looking at this, your overall function is square root, right? But inside it is a 1 minus x squared. So when there's stuff nested, they're composite functions. Okay. So this one again is a product rule. We have an x squared times a square root, right? So we have to do first times the derivative of the second plus second times the derivative of the first, right? So if we rewrite this as f of x equals x squared times 1 minus x squared to the 1/2 power, that will enable us to use power rules, right? Now I'm ready to take my derivative. So f prime of x is the first function, right? Times the derivative of the second function, which is negative 2x. Okay? Okay, so that's first times the derivative of the second plus second, which is just 1 minus x squared to the 1/2, times the derivative of the first, which is 2x. Okay? So that's our product rule. So now we've got a lot of wackiness going on, don't we? Over here, we've got a 1/2 times a negative 2, right? And an x in there. So 1/2 times negative 2 is a negative 1 times x. So that's negative x times x squared. So that is negative x cubed. Is everybody good? I just tackled multiplying the x squared times the 1/2 times the negative 2x. Okay? And that all goes over, because the 1 minus x squared has a negative exponent, my 1 minus x squared to the 1/2. Okay? Now let's tackle the next set of stuff over here. And there's not much I can do about that, right? So it's just going to be 2x times 1 minus x squared to the 1/2. So I've got a fraction plus a not fraction. And I want to add them together, which means I need common denominators. How do I get common denominators? Multiply by the denominator over itself, which is 1 minus x squared to the 1/2 over 1 minus x squared to the 1/2. So when I do that, this times this just becomes 1 minus x squared. And that becomes over, I'm just going to write it as square root of 1 minus x squared. So now I'm going to distribute so that I can combine terms and smush these things together. So that becomes negative x cubed over square root of 1 minus x squared plus 2x minus 2x cubed over square root of 1 minus x squared. We good? And that becomes 2x minus 3x cubed over square root of 1 minus x squared. And they really like to factor that out as much as we can. So we have x times 2 minus 3x squared over square root of 1 minus x squared. And that is the final answer. Why? So it's down to one term. So factor it whenever possible. The thing that you do get out of the factoring is sometimes you can cancel. It's rare.
The answer on the left would be like partial credit then?
Well, the deal is you get multiple choice tests. Oh, so you have to know. I mean, I suppose if you wanted to take a shortcut, you could graph all 4 answers and your partial answer, but I don't really think that's a shortcut.
Just real quick,
Mhm.
the negative 3x cubed is the negative 2x times the half, right?
I got this, negative 3x cubed. Is that what you're asking about?
Negative 3x cubed over 1 minus x squared to the half power. Negative x cubed. I'm just still trying to figure out.
You're right here?
Yeah.
Oh, okay. How I got from here down to there?
Yeah.
Okay, so I took negative 2x times x cubed, x squared, right? Times 1/2.
Okay. All right.
Okay. So lots of stuff going on in these. The hardest part is being able to see what to do and realize that there's not one right way to get to the right answer. Okay? Some of the stuff you might do in a slightly different order than me, and that's okay. As long as you're doing the rules properly, sometimes the order doesn't matter so much. Okay?
We did that because we know that 1 minus x squared is going to the denominator.
Mm-hmm.
So it just leaves
Yeah.
in the brackets 1/2 negative 2x x squared.
Mm-hmm. And I put it in brackets because I knew there was going to be a bunch of stuff in there. It just kind of differentiates a little bit more, no pun intended. And here they do another quotient rule with example 8. I think we've done enough quotient rules because we did one with that on 28 when we did that example. Example 9 is kind of interesting, so let's go through that. I'm not going to torture you too incredibly much until we take a break and then do section 5, or at least part of it. Because I really think getting through part of section 5 before the long weekend allows you to do most of the homework, you know, and then you can leisurely study for the test and perfect it. Okay. So we have an overall structure of something to a power here, don't we? But inside, oh dang, quotient rule, right? So when we go to take that dip, we know the dip's going to be implementing that quotient rule. Are you with me on this? Okay. So when you look at these things, kind of look at the structure. What am I looking at? What's the overall picture? It's going to help drive what you do. Okay? Because the hardest thing to know how to tackle these problems is, what the heck do I do? You know? Okay? So look at that overall structure. See what it is. Is it something times something else? Is it something divided by something else? In this case, the overall structure is something to a power. Well, that's easy. But inside it is a quotient. But the inside stuff is just the dip, right? So we just expect to do that quotient rule as part of our dip, okay? So here we go. Y prime is going to be 2 times stuff to the first power, right? Times the dip. Okay. Low, d high. What's the derivative of 3x minus 1? 3. Minus high, d low. What's the derivative of x cubed plus 3? It's 2x. Over low squared. Okay? So, and I think we can just kind of distribute and all that goodness in here. So we'll have 3x squared plus 9 minus 6x squared plus 2x all over x squared plus 3 squared. And then here I just have Okay, now we can combine some terms. So I have negative 3x squared plus 2x plus 9 all over x squared plus 3 squared times okay. And if I truly wanted to keep it as one term, I've got the same stuff on the bottom, right? So on the bottom of this, I'm just going to have x squared plus 3 cubed, right? And on the top, I'm going to have 2 times 3x minus 1 times negative 3x squared plus 2x plus 9. And that is your fully factored final answer. Questions from Zoom land? Okay, I take that as a no. Okay, now we're going to talk about trig functions and the chain rule. So, just like if we said the derivative of sine x was cosine of x, the derivative of sine of some function u is cosine of that function u times the derivative of u, okay? We would always say cosine u du, right? For the derivative of u. So nothing has really changed, except we have to remember the dip, okay? So that u prime, that is the dip, the derivative of the inner function, okay? Okay. So for instance, if we have sine of 2x, my u is 2x, right? What's the derivative of 2x? 2, right? So I have cosine of the u times the derivative of it, which becomes cosine 2x times 2, which is just 2 cosine 2x. Okay? Same with cosine of x minus 1, right? But what's the derivative of x minus 1? 1, okay? So it's not going to look like anything different because the derivative of that inner function was just 1. And that's okay. So we're just going to have negative sine of x minus 1. Okay? We already showed you a tangent on this. So the derivative of 3x is 3, right? So this derivative of tangent is secant squared. So we have secant squared 3x times 3, which is just 3 secant squared 3x. Okay? So just remember that dip. And here is a summary of all the differentiation rules. Okay? This is what needs to be on your formula sheet. Okay? Now, one other thing that I want to cover with us is repeated application of the chain rule. something like this. So we would see this as sine of 3x to the third power. Okay? That's how you have to see that. So f prime is then 3 sine of 3x to the second power, right? But what's the dip? All of this, sine of 3x, another composite function, huh? So what's the derivative of sine of 3x? Well, it's sine of 3x times 3, or 3 sine 3x. Okay? So this becomes 3 sine 3x squared, right? Times another 3 sine 3x. Okay? So if I was writing this out, oh, derivative of sine is not sine, it is cosine. There we go. So this becomes 9 sine squared 3x cosine 3x. Okay. I think it was after 9 o'clock. It's not. Let's see. Trying to see if there's anything I could give you that I haven't already talked about. I think we're pretty good. When you're doing the homework, along about problems 71 through 92, there's a bunch that talk about equation of a tangent line, and I can't remember exactly what I've assigned for this. Let me check and see. Of course, I made sure to talk to you guys about the 2 different ways that we can express equations of mathematical relationships. One was explicitly, where y equals something, right? Or f of x equals something, right? Where we know all of our output. But the other way was implicitly, okay? Now, implicit function, or I use the term functions loosely because a lot of times they're not functions, right? Think about conics. Are conics functions? No. But how would I find the slope of a tangent line to a conic when it's not a function? So far, none of what we've covered in taking the derivative has covered things that aren't functions yet, huh? Okay, well, welcome to implicit differentiation. So here we cover how to take derivatives of stuff that isn't functions. We still need tangent lines to the curves of those too. So we're going to talk about distinguishing between functions written implicit and in implicit form and in explicit form, and then using implicit differentiation to find derivatives. So explicit form has a y equals, okay? Implicit form does not. Now, sometimes you say, well, I could just solve for y. Yes, sometimes you can. Sometimes you can't. Or sometimes it's so very difficult that you wouldn't want to take the derivative after you were done. You know? So we have implicit differentiation. Okay. So how would we find the derivative of y with respect to x for this function here? Not possible to solve for y, is it? No. So we're going to need to use implicit differentiation. Now, understanding how to do this is understanding that all of our differentiation is taking place with respect to x. Okay? This means that when you differentiate terms involving x, and only x, you can differentiate as usual. Okay? When you differentiate terms involving y, you must apply the chain rule, because you're assuming that y is implicitly defined as a differentiable function of x. So I'll show you what that means. So when I'm differentiating x cubed with respect to x, great, fine, all these variables are great, okay? However, when I'm differentiating y cubed with respect to x, okay, I'm going to have to apply the chain rule. So I'm going to have 3y squared, right? But I don't know what that dip is, right? What's the derivative of y with respect to x? I don't know, but that's my dip. So I just tack on a dy dx is what it generally amounts to. Okay? Yes. Okay? Here, I can take the derivative of x is 1, but the derivative of y, 3y, is 3 dy dx. Right. Okay? So, I'm going to do a little bit of erasing here.
So later down the line of the map, will we find the derivative of y, or is that just not?
Yes.
Okay, cool.
Okay. This is where a lot of the things that you've been taught in college algebra and a lot of the techniques that you've been taught, they're all going to come together in this lesson. It's like, oh, it's a beautiful thing. Okay, so here we have, what's the overall structure of xy squared? Right, two things multiplied together, which means we need to use product rule, right? So we have the first function is x, the second function is y squared, right? So we have the first function x times the derivative of y squared, which is 2y, and the dip is dy dx, plus the second function y squared times the derivative of x, which is 1. Okay? So this just becomes 2xy dy dx plus 1. Now, we're not done with the problems yet. Okay? So, let's look at the guidelines for implicit differentiation. First, we are going to differentiate both sides of the equation with respect to x. We are going to collect all terms with a dy dx on the left side and move everything else to the right. We will factor dy dx out of the left side and solve for it. Very rarely in calculus do you get a list of steps this explicitly. So we explicitly tell you what to do for implicit differentiation. Ah, the irony. Mask. Okay, so let's see what that looks like. So you will actually get an equation, a real life actual equation. You will see that this equation has a left side and a right side, and you're going to differentiate both sides. Okay, so the left side has 4 different terms that you're going to have to differentiate each of them, right? So 3y, what's the y cubed, what's the derivative? 3y squared dy dx. What about y squared? 2y dy dx. Minus 5y, what's that? And then derivative of x squared becomes negative 2x, and the derivative of negative 4 is 0. Easy peasy?
Sure.
So then, the stuff without a dy dx, which is what? That, only that in this one, moves over. So we end up with all of this. Oh, shoot, stop that. Equals 2x, right? Then we're going to factor out dy dx. And we end up with 3y squared plus 2y minus 5 equals 2x. And then how do you suppose we're going to solve for dy dx? I just need to get dy dx by itself to solve for it. Divide. Yeah, divide by all that stuff on the left side. So dy dx is 2x over 3y squared plus 2y minus 5. And that is your derivative.
Would there ever be a situation where there are y's and x's on both sides of the, then you have to move them over before you can differentiate both sides?
Just differentiate them where they're at and then move them. Make things harder on yourself. This is one of those rare examples where we actually give you a really complicated one as your first problem, because you get to see how it works. There's not, you know, we've got 3 dy dx's, you know. Okay. So the original equation looked like that. Wouldn't that make a nice vase or something like that? That was the original equation. You can see that is definitely not a function.
Fails the vertical line test.
Yes. Okay. But my derivative, this, allows me to calculate the slope of the tangent line to the curve along any point on that function, or on that vase.
So you just plug in a point.
Yeah. So if I have a point on the function, like 1, -3, I can plug in the 1 for x and the -3 for y, and that'll calculate the slope of the tangent line. Okay?
That's crazy.
Now, you have to know the whole point.
Yeah.
You can't just know an x. Okay. because it hurts my eyes looking at that stuff too. Okay. So we want to determine the slope of the graph of this at the point 3, 1, which means we're going to find the derivative and plug in 3, 1, right? So my function is 3 times x squared plus y squared squared equals 100 x, y. Oh, yeah. Oh, yeah. So you see that whole left side is like a power thing, right? Okay, so we have 3 times something to the second power, which means when I take the derivative, it's going to be 6 times that something to the first power, right? Okay, and then times the dip, which is the derivative of the inner part, which is 2x plus 2y dy dx. I don't put the dy dx in there until I actually try to take a derivative of y. That first time I didn't take the derivative of y when I put that y squared, so I don't have to worry about putting a dy dx with it. Okay? And I'm done. That wasn't bad. Now, the second half of it, the right side, is what? What's the overall structure of it, though?
Oh, 100 times x.
Yeah, so it's, what kind of thing are we going to have to do? Product rule. Very good, because it's a product. See why I teach you to learn to see the structure. Okay? So I'm going to look at it as 100x times y. Okay? We good with that? Okay. So what's the derivative of 100x? Okay. What's the derivative of y? dy dx. So I've got the first times the derivative of the second, which is just 1 dy dx, plus the second times the derivative of the first, which is just 100. Because it's the first times the derivative of the second, plus the second, y, times the derivative of the first. Okay? You with me?
In the book, they're saying plus y is times 1.
There's 100 in each of those.
Okay, so the book just started different.
Same thing.
Sorry.
That's all right. Okay. So now we have to mess with this left-hand side. So I'm going to take and FOIL everything out because I've got to get it to terms, right? So I'm going to take and do these two first and then multiply everything by 6. That's my way that I thought I'm going to do it. You might want to multiply everything by 6, multiply the first one by 6, and then FOIL it out. Your choice. Doesn't matter to me. Okay? So I'm going to have, let's see, 6 times 2x cubed plus 2x squared y dy dx plus 2x y squared plus 2y cubed dy dx, right? So that gives me 12x cubed plus 12x squared y dy dx plus 12x y squared plus 12 y cubed dy dx equals 100x dy dx plus 100y. Now, I've got 3 terms with dy dx's and 3 without. So I'm gonna swap them all. I'm not gonna show much work in this because quite frankly, I'm getting tired of writing. And you're gonna get that way too, right? So I'm gonna factor at the same time if you don't mind. Okay, so I'm gonna have a dy dx times 12x squared y plus 12y cubed minus 100x equals 100y minus 12x cubed minus 12xy squared. Did everybody follow what I did there? I knew my next step was to factor, so I just did it all at once. Okay, now the last step is to divide. So I've got dy dx, nope, I've got dy dx equals this stuff. Oh, I didn't mean to do that. I'm just going to have to write it. Over so that's my derivative, and I want the slope at the point 3, 1. So that is going to equal, stop that, what is going on? Is 100 times 1 minus 12 times 3 cubed minus 12 times 3 times 1 squared over 12 times 3 squared times 1 plus 12 times 3 cubed, 1 cubed even, minus 100 times 3. And it will all be a nice, lovely thing of 13/9. When you do all that. Mm-hmm. Did I not put, I didn't put section 6 in here, did I? Dang, okay. I'll have to remember that for next time. I forgot to add section 6. Okay.
So they factored out the total.
Now, I'm not quite done yet. I just think I'm done.
Did you factor out the 12x like they did?
No, I didn't. They factored out x squareds and y squareds, and I just did it differently. It doesn't mean it's wrong. Okay. Example 7 is really important because you need to find second derivatives sometimes. So x squared plus y squared equals 25. Find the second derivative. Okay. So first derivative, easy peasy, right? Derivative of x squared is 2x. Derivative of y squared is derivative 25, 0. What do we do? Yeah. So dy dx is equal to negative 2x over 2y, which is just negative x over y, right? Easy peasy. Now, we want to find the second derivative. How do we find the second derivative? We take the first derivative and we take the derivative. Now that this one here, though, yes? Why is the what in front of the y? Because that's just the notation. It's weird. That's why in this problem it uses some different notation just to kind of sneak it in there so you know that it's, because math wars. Okay. No, it is correct. Now we find the derivative of that, right? So my second derivative is equal to low d high, right? Minus high d low over low squared. Okay. Now, do I know what dy dx is? Yes, I do. It's that. So we have negative y plus x, after we simplify it, times negative x over y squared. Okay, which gives me, and I'm going to multiply this by y over y. Okay, are we good with that? So this is going to give me negative y squared over y minus x squared over y squared, right? I'm just doing complex fractions, that's it. I multiplied this one here by y over y, just so I could have common denominators. Okay. And then I'm going to have, so that's the negative of, I'm just going to say x squared plus y squared over y squared over 1, right? Which when we go to clear that bottom fraction, we flip and multiply, right? And so that becomes negative of x squared plus y squared, it's a y there, over y cubed. But we also know that x squared plus y squared is 25. So that's negative 25 over y cubed.
So why is it a 1 under the y squared?
Because I felt like it. So I could show you the flip and multiply.
Oh.
You could write it as just over y squared, but then it's harder to see it as a fraction divided by a fraction. So I made it look like a fraction, so you could see it was a fraction divided by a fraction. So there's a lot of weird substitution that comes in with second derivatives and implicit differentiation. And you kind of need to see that so that you're not taken aback by it and kind of get stuck in the middle of a problem. Okay? And that is all I have. So that gets you to the point where you can pretty much do everything except the word problems. So when we come back next Wednesday, we've got section 6, which is not terribly long, but it's word problems. Everybody's favorite. So yeah, we'll have some fun with word problems. And we'll probably do some of the review exercises out of the back of the chapter too, you know, just to kind of make sure everybody knows how to do some stuff, you know. Okay. So that's all. If you have questions, don't hesitate to ask. This is a great time to ask questions.